Okay, we're in video 20B. Going to look at an example with hypothesis testing for a mean. So let's pretend that we work for Consumer Reports magazine, and we planned on recommending Continental DWS tires with the 50,000 mile warranty next month, unless our sample of size 20 tires convinces us that Continental is not truthful in their claim that the tires last 50,000 miles. So we will test the population mean tire tread and see what we think here. So first, what conditions must be met before we proceed, given our limited information? So for one thing, keep in mind that the variable here is how long the tires are going to last, so that's a quantitative variable, so this is a mean problem. Our sample size is a bit on the small side, this limited information here. So our sample size is only 20. We're testing 20 tires. Those 20 tires do have to be an unbiased sample. And because the sample size is on the small side, it's under 30, we would also have to graph the data and make sure that our histogram had a normal looking shape to it there. So since that sample size of 20 is under 30, you should graph the data. Looking to make sure, a normal model is appropriate. If you graph the miles on those 20 tires and the data are skewed right, then we would stop here. The conditions would not be met. We need to go collect some more information. As long as they look pretty unimodal, symmetric, we'll be okay, even though we have a small sample size. Okay, how about our hypotheses? Again, we're looking at how long the tires last in miles, which is quantitative, so we're testing a mean. Continental says they're going to last 50,000 miles, so we will assume that that's true. And then we're going to recommend the tires unless we find out that this isn't true. Well, if they lasted longer than that, we'd probably still recommend them. But if they last less than this, then we wouldn't be real happy about that. We wouldn't recommend the tires. So we're looking to see, can we find evidence that the average number of miles that these tires last, is it less than 50,000? So we'll assume it's 50,000 miles, and we're going to be looking to see, can we find evidence that it's actually less? If it's less, we won't recommend the tires. Okay, let's go to part C. So one member of our team claims we don't have to run the test because the sample mean for those 20 tires, you've got it in your notes here, is Y bar, the sample average for those 20 tires is, let's say, 49,464 miles. That's less than 50,000 miles, case closed, don't need to run the test. Of course it's less, right? So explain the faulty logic with this member of our team. For one thing, if the true average is 50,000 miles, think about your normal curve. Half the time the tires will last longer than that. Half the time the tires are going to last less than that. They're not always going to be spot on. We do have variation, a standard deviation to that set of data. So half the time they're going to last less than 50,000 miles, for one. The sample mean must be convincingly smaller than the average for us to say that we're not going to recommend the tires. So a couple things here. Even if the average is 50,000 miles, half the time the tires will last less than that. Half the time they'll last longer than that. And so our sample mean would have to, again, be convincingly less than that in order for us to not recommend the tires. Now, what's convincingly less? You know, we look at this, and this is just over 500 miles less. You know, is that significant or not? Part of that would seem to me not to be that much of a significant difference there, but part of this is going to depend on what the standard deviation is, which I don't think we've revealed yet. So we'll eventually see here that, you know, we're probably not convinced with just slightly over a 500-mile difference there that they're significantly less. So let's continue with the problem and see what we think about that here. Here's the standard deviation. So from the sample, we had a standard deviation, which is very important, of 3,322 miles. Finish the hypothesis test and make a conclusion. And we're given a level of significance of 1%, or alpha equal to 0.01. So now we're ready to actually conduct that test. We have our hypotheses. Let's go ahead and get our test statistic and our p-value. So this was a mean problem. So for your test statistic, you're going to compute a t-test statistic, where you look at the sample mean, see how far that is from the hypothesized mean, divide by the sample standard deviation, divided by the square root of n. And we have all these numbers here. So in our sample, the tires lasted 49,464 miles. Our hypothesized average is 50,000 miles. The standard deviation is 3,322 miles, divided by, we took a sample of 20 tires. Just be careful, make sure you take the whole numerator, divide by the whole denominator. And when you do this, you ought to get a test statistic of negative 0.0722. So it would appear that this is not very far below the average here, given that the value of that test statistic. We'll go ahead and we'll compute the p-value for this test statistic. I recommend you draw a picture for those p-values. Here's t. Remember, a t-value of 0 is in the middle. We're a little bit negative here, so our test statistic is negative 0.722. We were testing that the average is less than 50,000. So from my test statistic, I'll shade the area to the left, since it was a left-tailed test. And this area right here, that is the p-value. For this, I'd recommend you use StatCrunch. Get on to the, go to those calculators, use the t calculator. You're finding the area here where t is less than 0.722. Just keep in mind with this one, you'll need to enter the degrees of freedom. Degrees of freedom will be your sample size minus 1, so the degrees of freedom is 19. And you're finding the area below here. So I'm going to give you that to you from StatCrunch. Pause the video, make sure you can get that. From StatCrunch, this p-value is 0.2395. So here's our test statistic. Here's our p-value. We were to test using alpha equal to 0.01. Almost didn't even need a significance level with this one. Clearly that p-value is bigger than alpha. This is not a small p-value. And so you should know that when your p-value is not small, that you're going to fail to reject the null hypothesis. And then finally, we've got our test statistic, our p-value. We've sort of made a decision here. Make sure you can write a conclusion in the context of the problem stating what this means. We failed to reject the null hypothesis. We didn't prove that the tires are lasting 50,000 miles, but we certainly didn't find any evidence for the alternative. We didn't find evidence that they're lasting less than what the company says. So we have no evidence that Continental isn't meeting their claim of 50,000 miles. I think I'll squeeze this up here. Sorry, I'm going to come down here. 50,000 miles. In your notes, you have plenty of room. You should just write that right below here. But our conclusion in context, we have no evidence that Continental is not meeting their claim that the tires should last on average 50,000 miles. All right, so that's the hypothesis test part of this problem. I believe in E, we're going to focus on this p-value and talk about what that means. So I'll flip the slide and erase this in a second, but we're going to interpret that p-value. Keep in mind what that p-value is. This is what we had in our sample. In our sample, the average was 49,464 miles. How likely are you to get a sample like that if the true mean really is 50,000 miles? That's sort of what the p-value tells you. The p-value tells you how likely you are to get a sample mean like this, or one even less, if the true average really is 50,000 miles there. So let's clean this up and we'll write that up. So if the true mean really is 50,000 miles, we get a sample mean like ours. Which was 49,469. Or even lower. With a probability of 0.2395, or almost 24% of the time here. Something that happens almost 24% of the time, that's not unusual. And so we have no compelling reason then to reject the null hypothesis that says that the average really is 50,000 miles. So this is not unusual at all. When that p-value is small that you begin to doubt the null hypothesis and find evidence in favor of the alternative. But this p-value is not small at all, not even close. All right, a couple more parts. We're going to tie this in with confidence intervals. So F, support your conclusion with a 99% confidence interval for the true average number of miles that these tires last. So now we're doing a confidence interval, still a mean problem. Keep in mind your formula for a confidence interval for a mean. We take the sample mean plus and minus a critical t multiplied by the sample standard deviation divided by the square root of n. Most of this we know. I'll leave a hole here for a second for the t-value, but the average was 49,464 miles. I'll leave a pause here for t for just a second. Our sample standard deviation was 3,322, and we sampled 20 tires. So you need to fill in that critical t value. Hopefully you can pause right now without any other advice and fill that in. If not, listen for a second and then pause and still get it. Remember that critical t is based on how confident you are and degrees of freedom. So you ought to be able to go to StatCrunch and use that t calculator. And figure out what that t value is. Since the sample size is 20, the degrees of freedom will be 19. And keep in mind what the area of those tails are. But you ought to be able to get that. From the t calculator on StatCrunch, that critical t is 2.861. If you can't get that, go to class and ask your instructor. You ought to be able to get that by now. All right, let's get the margin of error. So just simplify this side. This over here is 2,125. And finally, if we take our sample mean plus and minus that, we'll have our confidence interval. So your interval goes from 47,339 miles up to 51,589 miles. And to sort of tie this back to the hypothesis test, we wanted to know if on average they last 50,000 miles, and you'll notice that 50,000 is a plausible value. It's inside that interval. So just a note here. It's inside that confidence interval. The results of your hypothesis test and your confidence interval should agree. They should not disagree. If you constructed a confidence interval and it went from 47,000 miles to say 49,000 miles for this problem, hopefully you would look at this and say, wait a second, I thought that we agreed that the average could be 50,000 miles. That disagrees with the conclusion of my hypothesis test. Go back and check them. One of them wouldn't be correct. So your results should agree. All right, a couple more parts to this one. What's the margin of error? Just did this. Margin of error you just did, 2,125. So that's part G. So right from what we just looked at, that comes into play where we get to H. What if Consumer Reports wants to get that margin of error down? They want it to not be 2,125 miles, they want it to only be 500 miles. To really see more precisely just how long these tires last on average. So they want a more precise interval. We could get a more precise interval by changing the sample size, and you should know that if you want to shrink your confidence interval there, get a more precise confidence interval, that's going to require more data. So we had sampled 20 tires. I'm sure we're going to have to sample more if we want to reduce our sample size. But let's figure out what the sample size would need to be. So this question's not get a confidence interval, not do a hypothesis test, but what size sample do we need? Keep in mind the formula for sample size for a mean problem is take a critical z times your best guess for the standard deviation divide by the margin of error that you want and take that entire thing and square it. Okay, so the critical z-score, how confident are we? We want to remain 99% confident like we were back up in F. And so a a critical z-score when you want to be 99% confident is 2.576. If you can't rattle that number off, that's okay. Use the normal, the z calculator in StatCrunch, and you ought to be able to get that. This is based on being 99% confident. All right, our best guess for the standard deviation in this one is going to be that sample standard deviation that was given. And the sample standard deviation was 3,322. And then for margin of error, we'd like to get the margin of error now to only be 500. And we'll square that entire thing there. If you simplify this, we get that n is 292.9. Regardless of what this is, you always round this up. And so we would need to sample 293 tires. And so you'll notice here, to become a lot more accurate with our estimate, we're going to have to go from only sampling 20 tires to sampling 293 tires, a much, much bigger sample size. My note here tells me that it's like 14 to 15 times as many tires as 20 tires in order to increase the accuracy there of our confidence interval. So sometimes this is something you'll have to decide. Is it worth it to be that accurate? Could you settle for a margin of error perhaps somewhere in the middle here where you wouldn't have to go through quite so much testing? That's a lot of tires to test. But this was a nice problem, went through sort of everything with means, from hypothesis testing to confidence intervals to sample size. And I believe that's the end of this one. So we'll see you in class. Thanks.